Hello friends, welcome to video lecture on dynamics of machinery. In the today's lecture, we'll discuss about numericals on free undamped single degree of freedom system. That is next part from this topic. So let us start. YouTube open to atmosphere at both ends contains column length L of a certain liquid. Find the natural period of oscillation of the liquid column. So this one YouTube manometer is given like this one. So this indicates the level of equilibrium. Okay, and here the displaced fluid whose area is shown by this hatchet portion. Okay, so what's about this one? When the liquid moves in upward direction, the resisting force will act in downward direction, whose magnitude is nothing but the FD. So what's about this one? Accelerating force with us, whose magnitude mx double dot with us. So this is nothing but the resisting force, or the force occurs for the moment of this fluid in vertical direction. Okay, that will comes in downward direction. So in this case, let the mass of the displaced fluid be md. Okay, so what's about this md? md is nothing but density multiplied by volume of displaced liquid. So we know the simple relation for the density. Density is nothing but mass per unit volume. Okay, from that relation you can get the md equals to density multiplied by volume of displaced liquid. So what's about the density? We can consider that density by liter or rho. So what's about the volume of the displaced liquid? For that, concentrate on this diagram. So what's about that term? That is nothing but here cross section area of this portion multiplied by this one length. So length you can get in terms of 2x, and cross section, we'll just consider that cross section as small. So in this way you can get the relation for displaced fluid, that is md equals to rho density multiplied by the volume of the displaced liquid, that is a multiplied by 2x. So the force exerted by the displaced fluid is nothing but Fd equals to, what's about this one? This is nothing but the mass. If we multiply by this mass by g, we can get the force. So what's about this one? 2x, that term written as it is, and rho into a, okay, multiply by g term written as it is. So consider the free body diagram of the liquid column as shown in figure B. So just focus here. Okay, so this is nothing but the displaced fluid. Okay, where 2x is nothing but here length, and here Fd is nothing but the force applied. This indicate the accelerating force. So easily you can apply here Newton's second law of motion. So what's about here? This indicates the accelerating force, and this is nothing but the resisting force. Okay, so we know the Newton's second law of motion. Accelerating force equals to summation of external forces. So from Newton's second law of motion, we can just see the direction for that accelerating force in vertical direction. So consider the negative sign for the same. So mx double dot plus Fd is in downward direction with a positive sign for this Fd. So where this mass m, already we get the relation for that mass m. Okay, from this step, rho into a multiplied by this 2x. 2x indicate the column length. So you can just replace that 2x by L. Okay, so what we get here? You should replace this mass m by this term rho into a into L. So minus rho into a into L multiplied by x double dot will remain as it is. So what's about the next one? Fd. Fd from the previous step, Fd already with us. Fd is nothing but 2x into rho a multiplied by g. This term should be written as it is. Okay, so in the next step, if you look towards right side and left side, rho a is common, so both this term, this one and this one, get cancelled. So what's about this x double dot? X double dot, just take this term towards the left side, and every term will becomes here positive. So rho a already get cancelled. So here x double dot into L will remains plus 2g, 2 into g, x will remains as it is divided by L written here. So if I take this L from here, so L should be goes in denominator equate with the 0. Simply equate this equation with the SHM. What we get here? Omega n equals to square root of 2g divided by L. Further we can get the frequency like this one upon 2 pi square root of 2g divided by L. And what's about the time period of oscillation? Time period of oscillation, you can get the reciprocal of this frequency. So reciprocal of this frequency is nothing but 2 pi into square root of L divided by 2g in terms of second. Let us start the next problem. A cylinder of mass small m and the radius r rolls without slipping on a cylindrical surface of radius capital R. Find the natural frequency for small oscillations. So system is like this one. Here the cylinder of mass m and radius r rolls without slipping on a cylindrical surface like this one, whose radius is nothing but capital R. Our ultimate aim is to find out the natural frequency for the small oscillation. So from a figure we can get this relation. As a small cylinder rolls without slipping, we can get this relation arc C dash P dash must be equals to arc C C dash. Okay. Now look towards this diagram carefully. As per our previous statement, arc C dash P dash, arc C dash P dash, okay, small portion of this one, okay, R portion, and next one arc CC dash means this one CC dash. When this start rolling on this surface, so this arc C dash P dash must be equals to arc CC dash. Okay, so from this can we write it this way? So what's about this angle? I'll just say this angle is nothing but the phi. Okay, so what's about radius for this cylinder? Radius we are considered as r. Okay, so what do we get here? R into phi, because the radius for this portion with us r, and this angle with us phi. So what's about the length for this one? Our arc C dash P dash, this arc C dash P dash is nothing but small r into phi. Similarly, if you look towards the next relation with us, arc C dash C is nothing but, what's about the radius for this bigger portion with us? Radius with us capital R. Okay, so capital R multiplied by theta. Okay, now look towards the, so in this way we can get the relation arc C dash P dash must be equals to arc CC dash, and we can get in this way small r into phi equals to capital R into theta. So what do we get for this capital, what do we get for this angle phi? Angle phi is nothing but r theta divided by small r. So if we differentiate this one, what do we get? Phi single dot equals to r theta single dot in divided by r. Now by using the principle of energy, what's about the principle of energy? U is nothing but kinetic energy plus potential energy. So in this case, kinetic energy due to two types of motion. First one, oscillatory motion, and second one, rotational motion. So what's about this oscillatory motion? So assume that the cylinder of mass m oscillate about O, similar to simple pendulum of length here capital R minus R. Now look towards this one. So assume that this cylinder, this cylinder oscillates about this point, okay, O point, similar to that of simple pendulum. Okay, so what's about the length for this one? Length capital R minus small r. What's about the kinetic energy possessed by this cylinder during oscillation? So we know the kinetic energy is nothing but here whatever the mass of this one. So in short, the mass moment of inertia of this one for the disc or for any cylinder, we know the 1/2 mass multiplied by its radius square. So here the radius with us, this portion, this indicate the radius of the rotation for or oscillation for this cylinder. The radius with us capital R minus small r. So in this we can get the relation for the kinetic energy possessed by the cylinder during the oscillation. So what's about the kinetic energy here? 1/2 multiplied by mass. This term indicate the mass moment of inertia for that cylinder. 1/2 mass multiplied by the radius with us. That radius indicate the difference between both the radius, means here capital R minus small r whole bracket square multiplied by velocity during the oscillation, theta single dot square. So what's about the rotational motion? Or rotational, since the oscillating motion is already taken care of, we have to consider the relative rotational velocity to find the kinetic energy possessed by the cylinder during the rotational motion. Okay, so for that, what's about that kinetic energy possessed by the cylinder during the rotation motion? For that, we have to consider the relative velocity. So relative velocity is nothing but the difference between phi single dot minus theta single dot. Okay, so theta term we have considered for the oscillations of that particular cylinder about O point. Okay, here the oscillations of this cylinder about this O point. And next one, phi term we have considered for the rotational motion of this cylinder over the surface of this one cylindrical portion. So we need to consider the difference between the velocities. Okay, that is difference between this phi single dot and theta single dot. Now just move towards the next part. So see, the kinetic energy is nothing but 1/2, okay, multiplied by mass multiplied by velocity square. So velocity here we have considered the difference between the velocity during the rotational motion as well as during the oscillatory motion. So 1/2 I into theta single phi single dot minus theta single dot whole bracket square. So what's about the relation for this one? Phi single dot. So on the previous step already that relation with us, theta single dot equals to r into 3 phi single dot equals to r into theta single dot divided by r. So replace that phi single dot term by this term. Okay, so we can get the kinetic energy possessed by the cylinder during the rotational motion in this way, 1/2 I into, so what's about this term? You have to replace this one phi single dot by this term I into theta single dot divided by r. Okay, if I substitute here, so theta is common, theta single dot is common, so take this theta single dot as common. Okay, so we can get the relation for this kinetic energy possessed during the rotational motion. So what's about the total kinetic energy? Total kinetic energy is nothing but addition of kinetic energy during the oscillation motion plus kinetic energy during the rotational motion. So during the oscillatory motion, already that kinetic energy with us, 1/2 mass multiplied by difference between the radius capital R minus small r whole bracket square into theta single dot square plus 1/2 into I into capital R by small r minus 1 whole bracket square into theta single dot square. Okay, so for the cylinder we know capital I is nothing but 1/2 mass into its radius square. Okay, so in the next step we can get the total kinetic energy, that is kinetic energy equals to 1/2 mass multiplied by capital R minus small r whole bracket square into theta single dot square plus I should be replaced by that 1 half into mass multiplied by r square term. So 1 divided by 4 will occurs here, multiplied by m into capital R minus small r whole bracket square will come here, multiplied by theta single dot square. Okay, so after simplifying, what we get, kinetic energy equals to 3 by 4 into m into capital R minus small r whole bracket square into theta single dot square, like this one. Now to find out the potential energy possessed by that cylinder, because of the cylinder moves at certain height. Okay, so because of virtue of its height, so whatever the potential energy we get, so potential energy, we know the formula, mgh, E equals to mgh. So when I displace this one cylinder towards one side, so during this one, whatever the height we can get, okay, in this way. So other relations already with us, this indicate the total, this distance indicate the capital R, this distance is nothing but the difference between capital R and small r, so r minus r. So this we can just get from this small triangle form here. Okay, what's about this distance? This distance is nothing but the capital R minus small r into cos of phi. We consider this triangle. Okay, so potential energy gained by the inner cylinder because of the height h gained by the center of the cylinder. So what's about this one, potential energy mgh? So what's about this height h? Height h is nothing but distance oq, this distance oq with us, oq minus this distance os. So from geometry, what's about this oq? Oq is nothing but capital R minus small r. And what's about this OS? OS is nothing but this distance. Okay, so capital R minus small r into cos of theta. Okay, in this we can get the relation. Just move towards the next step. So capital R minus small r is common, just take this common. Okay, here whatever the part remains inside of the bracket, just write that part. Okay, so 1 minus cos of theta will remain. So what's about the potential energy? This term, this one, okay, that part will remain as it is. So this is nothing but the h term. Okay, so from this relation, potential energy is nothing but mg multiplied by this term indicate the h term. Okay, so what's about the total energy? Total energy is nothing but kinetic energy plus potential energy. Kinetic energy already with us, this term indicate the kinetic energy. So 3 by 4 into m small m into capital R minus small r bracket square into theta single dot square plus mg into this one capital R minus small r into 1 minus cos of theta. This term indicate the potential energy, this term indicate the kinetic energy. So kinetic energy already we get from this relation, this one already we have calculated that. Now once we get the total energy, next task become very easy. So differentiating this relation with respect to time t, and by using the energy method, what we get, du by dt equals to this term, you have to take the derivative of this term. Okay, so the 2 will come here, so 2 1 2 get cancelled here, the 2 will remain here. So 3 by 2 into m into, so what's about this one, capital R minus small r, these terms are constant, will remain as it is. What's about this one, theta single dot theta double dot will come here, so plus mg, this term will remain as it is. So derivative of this constant term 0, derivative of this cos of theta minus sin theta, minus minus becomes plus, again derivative of theta is nothing but theta single dot, equate with the 0. Next one, as theta is very small, so for this case we can consider this sin theta is nothing but the theta. Okay, so from this step what we get, this will remain as it is, 3 by 2 into mass m into this one capital R minus small r bracket square theta double dot plus mg into sin theta should be replaced by theta. So in this case theta single dot should not be equals to 0. Okay, if I take the theta single dot as common, so second bracket must be equals to 0. This is the bracket, second bracket, 3 by 2 into m into r minus r whole bracket square theta double dot plus mg into r minus r into theta equals to 0. Now rearrange this equation in a such a way that we can compare that equation with the SHM equation. Okay, so write this term, okay, theta double dot, or keep this theta double dot as it is, and take this term, okay, towards this side. So here m get cancelled, this r minus, okay, this term get cancelled, okay, only single r minus r will remains, okay. So we can just modify that relation in this way: theta single dot plus 2g divided by capital R minus small r into theta equals to 0. If we compare this one with the SHM equation, what do we get? Omega n equals to square root of 2g divided by 3 into capital R minus small r. Okay, we can get this term in terms of radian per second, and in terms of hertz we can get this relation like this one. Only 1 upon 2 pi will added in the previous step. Okay, we can get Fn equals to 1 upon 2 pi square root of 2g divided by 3 into capital R minus small r. Next problem, determine the M equivalent and K equivalent for the system as shown in figure when x, the downward displacement of the block measured from the system's equilibrium position, is used as the generalized coordinates. Okay, so here the system is given like this. The system consists of one pulley, just say this one as pulley, because on one side of this one spring is attached up, so whose stiffness with us 2k, and another spring is here whose stiffness with us k, mass is attached up, okay, at the end of that pulley was one side of this spring, okay, whose displacement with us here x. So here our aim is to find out this one M equivalent and K equivalent. First of all, get the potential energy of the system. What's about the potential energy possessed by the system? As we know, the potential energy is possessed by the springs. One half, we focus on this one, this spring. What's about the potential energy? One half K into x square plus one half, if you focus on this spring, stiffness with us 2k, so one half 2k, so displacement with us x. Okay, pull this one in downward direction, so same displacement will occur here, minor with us x. Okay, so we can get the potential energy of the system is nothing but one half. So what's about this one x square, this one, this term is common, one half term is common, so k plus 2k is nothing but 3k. Give equation number 1 for this one. So our aim is to find out the K equivalent and M equivalent. So we know the potential energy formula. Potential energy is nothing but potential energy equivalent is nothing but one half K equivalent into x square. This is the basic formula. Now compare this equation number 1 and equation number 2. Straightforward we can get K equivalent is nothing but 3K. This is the answer for our first point. Okay, so what's about the kinetic energy of the system? So kinetic energy of the system, if you focus on this mass one, this mass possesses the linear motion, or can just say the translatory motion possessed by this mass, as well as the torsional motion possessed by this pulley. To get the kinetic energy possessed by the system, it consists of translatory motion of the mass plus kinetic energy possessed by the torsional motion of the pulley. Now get the total kinetic energy. Kinetic energy is nothing but one half. If we consider the mass attached at the end of that pulley, so one half mass multiplied by x single dot square plus. So what's about this one? Kinetic energy possessed by the pulley, okay, during the rotational motion or translatory motion. So here one half I into theta single dot square. In this way the term will occur. So if you look towards this one, x and theta, the two different variables with us. So bring this equation in one variable. So for that we know x is nothing but r theta for the smaller displacement. We can get theta equals to x divided by r, and theta single dot is nothing but x single dot divided by r, like this. So if you just see this relation, we can just replace this theta single dot by this term. okay, x single dot by r in this way. What do we get here? Total kinetic energy is nothing but 1/2. The mass term will remain as it is, okay, plus what's about this one? I term will remain as it is, and this one, a square of this one will occur here. So r square is here. So take this 1/2 common from this side and here x from this side. So we know the equivalent kinetic energy is nothing but 1/2, or simple formula for kinetic energy. We know kinetic energy is nothing but 1/2 mass multiplied by velocity square. So if I give the suffix for this one as equivalent, kinetic energy equivalent equals to 1/2 mass equivalent into x single dot square. Now compare equation number 3 and equation number 4. What we get here? The mass term is here. Okay, this term and this term will remain the same. Okay, so this one same, this one same. So what we get here? M equivalent is nothing but m plus I divided by r square. In this way, you can get the relation for M equivalent. So next problem, similar to that of the previous one. Determine the M equivalent and K equivalent of the system as shown in figure. Consider x is the displacement of the mass measured from system's equilibrium position. Also find the natural frequency of the given system. So for doing the calculations of K equivalent and M equivalent, we compare this problem with the previous case. To get the K equivalent, what we did, we get the relation in terms of potential energy in case of K equivalent, and in case of M equivalent, what we did, we calculate the value of kinetic energy, okay, total kinetic energy. So here see the system is given like this, okay, system is resting on inclined plane, okay. So the potential energy of the system is nothing but the energy possessed by this spring. So what's about this one? 1/2 K into x square, okay. So x is nothing but here linear displacement for this spring, or linear displacement for this mass. So what's about the here, the simple single spring with us, okay. Straightforward, we can compare this relation with the potential energy equivalent is nothing but 1/2 K equivalent into x square. We compare both the equations. What we get here? Equation number 1 and equation number 2, we can get the kinetic energy. We can get here K equivalent is nothing but K in short, okay. In this way, we can get the relation K equivalent equals to K. Also, the kinetic energy in the system due to translatory motion of mass and rotational motion of the circular part, that is here the cylinder or the same mass. This is the cylinder or the mass is given. Translatory motion as well as a rotational motion of this mass should be considered. So here kinetic energy in the system due to translatory motion of the mass and a rotation motion of the circular part, that is the kinetic energy is nothing but here addition of kinetic energy during the translatory motion and during the rotational or torsional motion. So what's about the kinetic energy during the translatory motion? 1/2 mass multiplied by its velocity square. Similarly here, in case of rotational motion, you have to consider the mass moment of inertia of the given circular part. So here 1/2 I multiplied by theta single dot square, okay, that term will occur here. So we know for the smaller displacement the relation, this relation with us, x equals to r theta. Now in the next step, what we get? K equivalent equals to kinetic energy equals to 1/2 mass multiplied by velocity square plus 1/2 plus, so what's about this theta single dot from this relation we get x single dot divided by r whole bracket square, okay. So from this you can get kinetic energy equals to 1/2, the mass term will remain as it is, this term will remain as it is, this one r square will occur here. Take this x single dot common from both the terms, okay. So what's about the kinetic energy equivalent? Our simple formula for kinetic energy is nothing but kinetic energy equals to 1/2 mass multiplied by velocity square. Okay, so x single dot square with us here. We compare equation number 3 and 4. This term will remain as it is. This one half will remain as it is. Straightforward, we can get m equivalent is nothing but small m plus I divided by r square. So this is about the m equivalent. Now our next target is to get the frequency relation. For that we know the total energy. Total energy is nothing but kinetic energy in the system plus potential energy in the system. So kinetic energy, already we know the kinetic energy possessed by that mass 1/2 mass multiplied by x single dot square plus this is nothing but the kinetic energy possessed by that particular roller during the rotational motion. So 1/2 I into theta single dot square plus this indicate the kinetic potential energy 1/2 k into x square. Now bring this equation into one variable. Okay, so here x single dot this term actually written as it is. So what's about this one? Theta single dot should be replaced by x terms. So theta single dot will come like this one, x single dot divided by r equals to theta single dot. Okay, so this term must be replaced by this term, x single dot divided by r whole bracket square plus 1/2 this term will remain as it is. Okay, so 1/2 m this term. Okay, just rearrange this term by squaring this one numerator term and denominator term. Okay, other term will remain as it is. Now as per energy method, just differentiate this term. Okay, so du by dt equals to 0 for the constant. You should be if you take the derivative constant, that should be 0. Okay, so what's about the derivative of this term? The 2 will occurs here, 2 by 2 into m into x single dot. Derivative of this single dot will come here, double dot. Okay, x double dot plus again the 2 term will come here. So 2 by 2 into I into x single dot, x double dot will occurs here, divided by r square will remains as it is. So 1/2 k into derivative of this term x square is nothing but x will occur, x will come here. So 2 by 2 into k into x, then x single dot will occurs here. Now in the next step, simplify this one. 2 get cancel here, 2 get cancel. Okay, so what we get here, m plus x single dot into x double dot plus I, 2 get cancel, so I into x single dot into x double dot divided by r square plus 1/2. So this term here, k into x. Okay, this term with us, k into x single dot. Okay, and this should be equals to 0. Now arrange this equation in such a way that we can compare this equation with the SHM equation. So in the next step, you can get the relation like this one, x double dot into x single dot bracket m plus I divided by r square plus x, this one k into x single dot into x equals to 0. Here in this case the velocity never becomes 0, means second bracket must be equals to 0. In this case, by rearranging, we can write x double dot plus this term actually goes in denominator, so k divided by this term small m plus capital I divided by r square into x equals to 0. Okay, straightforward, compare this equation with the SHM equation. What do we get here? Omega n equals to square root of k by m, means here m plus I divided by r square in terms of radian per second and in terms of this one in terms of hertz, 1/2 pi square root of k divided by small m plus I divided by r square. Okay, this you can get the frequency in terms of hertz.